the time dependence and things like that, measurement, sudden collapse, etc. All that will not be part of your homework. So hopefully that is some sort of a culture that will remain with you. So let's start by talking about time-independent Schrödinger equation. Okay, so we will take the time part apart and we'll focus on the space part and see what it tells us. So let me just put so time-independent Schrödinger equation. Let's remember the time-dependent one. It was I h bar del over del t psi equals Hamiltonian times psi. Do you remember this? Yes? Hopefully not in the form of a nightmare, but in any case, psi was depending on both space and time, but we can actually do separation of variables here. So let's do that. We can represent it as space part times time part. Okay? And when you do that, after some algebra, which is, you have done this 1,000,000 times, okay? I don't want to bore you. You will arrive at this. Okay, this is time-independent Schrödinger equation. After some math. Okay? It's an eigenvalue equation. Remember the measurement. If you measure energy, you would get one of the energy eigenstates, right? So this is that equation. This is like for, if you have the Hamiltonian, you will have certain energies times the wave functions corresponding to those energies. Okay? So let's, for example, look at a simple example of this, so-called particle in a box. So if you have 0, A, and this is infinite potential outside, okay, and 0 potential inside. So it's a box of length A, and the particle is definitely inside. Now, what is Hamiltonian? Hamiltonian is potential plus kinetic, right? Inside, the potential is 0 inside. So all you have as a Hamiltonian is just minus h bar squared over 2m del squared over del x squared. All you have is kinetic energy. Did you follow so far? Yes? So since that's all you have, your equation becomes something like this. This is your equation subjected to boundary conditions, and the boundary condition is the fact that over here, since the potential over here is infinite, the particle is definitely not there. Okay, quantum mechanics has tunneling, right? But not into infinite potential, okay? Definitely, particle is definitely not there, definitely inside the box. So we have these boundary conditions. So,
like if the potential is infinite but a single point.
Yeah, okay. Then it's a different story. The question was, what happens if it's a Dirac delta potential? Then you can integrate this and you will get something like this. Good. Actually, that potential is a good model for atoms, right? Because atoms are like the nuclei, the positive nuclei is attracting negative nuclei with a force of 1 over r. So in principle, it's a rabbit hole that goes down to infinity. Okay? So that kind of needle-like potentials are good models, but we will not use them. We will use these square potentials. If you do the proper algebra, phi n come out as square root 2 over a. This is so well known that I don't want to bother you with this. Okay? So these are just sine. Why sine? Why sine? Can anyone tell me?
Means set boundary.
Yes. So it fits the boundaries, right? So when you write, so phi n at x equals to 0 is 0. Do you agree? Phi n at x equals to a is also 0 because sine of n pi over a times a is sine n pi. N is an integer, so it's going to be 0. But there is a further thing why it's not just any other function that gives you 0 at the boundaries, right? The other reason is that the second order derivative of this one, del squared psi n over del x squared, also has the same sine term in it, right? So because of that, it's proportional to this. Because of that, it's a solution to this equation. Hopefully this makes some sense. Okay, I want to go over this theory part quickly and reach at the computation part. But yeah, let's plug in. Let's actually calculate del squared over del x squared psi n. So what do you get? You get square root 2 over a, and you get minus n squared pi squared over a squared sine n pi over ax. Does everyone agree with this or not? I took twice the derivative of sine alpha x, so I got minus alpha squared sine alpha x. Good? Now if you plug it in, you have a question? No. If you plug it in, you will see that En comes out as h bar squared pi squared n squared over 2ma squared. Okay? It's a very well-known formula, that's why I know it by heart. But if you also plug it in, you will see that it is the case. Okay, so let's go back to our computer and look at the particle in a well. It's not really in a box, it's in a well, and it's not a really deep well. So let's start from the beginning, importing and some length and time scales, if you remember from previous part. Then I have this n, which will correspond. I'm actually going to use our Fourier transform knowledge here. I'm going to define some x that goes between minus L0 over 2 and L0 over 2, some box of length L. Actually, it will go between minus L over 2 and L over 2, but inside that box, okay, let me draw it for you. So we are looking at particle in a well, and this particle in a well system has x coordinates like this, and the coordinates are defined from minus L over 2 to L over 2, but within that we have potential that is 0 except for here there's a well. Okay, so this is minus V0 and this length is L0. Okay, are you fine with this potential? Let's see how this potential is defined. It's defined over here. We have a bunch of zeros, and between L0 over 2 and L0 over 2, we have minus V0. Do you have any questions so far? Okay, so let's remind ourselves there is this Fourier transform matrix, and if you take its conjugate transpose, multiply it with diagonalized ik's, if you remember, multiply it with Fourier transform divided by n, you will get the first order derivative matrix. Do you remember that? Yeah. Yes, you have used it in the homework if you have returned it. And dd, the second order derivative, is d times d. This is matrix multiplication. Okay. Now, the kinetic energy is h bar squared over 2m times the second order derivative. Do you agree with that? So we have the kinetic energy operator here. We have defined the potential here. And basically Hamiltonian is kinetic energy plus the potential energy. So far, do you have any questions? And remember, we have sent time away. We are just looking at energy eigenstates. We are just going to find the eigenvalues and eigenvectors of this Hamiltonian. And eigenvalues will correspond to energies. Eigenvectors will correspond to energy eigenstates. So far, any questions? No? These are some stuff that we will use later on, okay? Just ignore that part for now. Yes? Very good question. So we will start with a single well. Guess what we'll look at? We will look at a double well, okay? Then multiple wells, okay? That's why it's single now. Very good question. So right now our single well potential is like this. And let me just run this code. Okay. I'm plotting only the first few energy eigenstates. So let me make it deeper first. Let me make it like 30 and plot for you. And let me also take this to 5, let's say. Plot the first 5 eigenstates so that you can see it. Do you see at the bottom there is one hump? Then there's two, like there's like this, then the next one is 3, 4, 5. Okay, this is sort of like sine pi x over a, sine 2 pi x over a, but we didn't give to the computer any sines or cosines. It just comes out from solving the Hamiltonian. Okay, but let's go back. Let's go back to what were the values? 3 and 2, right? So let me run it again. And I'm only plotting the first 2 eigenstates. You can even ignore this one. So not all states need to be confined in the well. You know, if you have an infinite well, all states need to be confined in that well. Okay? But if you have a finite well, we have a finite well here, some of the states will just not be inside, their energy will not be below the top of the potential. Some of them will have higher energies than the top of the potential. And so they will be just signs floating at the top. Okay, so far do you have a question? So we will concentrate on this on this potential. Yes?
Can you do it now, like plot the 5 states?
Yes. Let me plot the 5 states. Also let me turn this widget on so that we can actually...
I wonder, does it like calculate the free particles as well?
Yeah. It calculates free particles as well. So for example, if you are going to plot 10 of them, so there is a bound state here. That's a bound state. It's not moving around. Think classically for a moment. if you have a car that has less energy than needed to go out, then it will stay inside the well. Imagine the well is like this, and the car wants to go out, but it only bounces back and forth. But if the car has enough energy to go out, these are those states that have enough energy that just only feel the potential, only kind of feel the potential, but otherwise they are free to, they are free to roam around. Depending on the depth of your potential, you will get a finite amount of bound states and actually infinite amount of unbound states. Okay? But if you have infinitely deep well, then all states are bounded. Not important. What is important is, let me tell you what I want you to take away from this. What I want you to think about is this well that looks like a needle. Think of it as the nucleus of hydrogen atom. Okay, the proton in the middle of hydrogen atom. It attracts electrons. So when electrons see them, they feel like a needle-like potential that goes down. Does it make sense? So the electron will go around it and will form this shape. Okay? Actually, if you plot the 1s state of hydrogen, let's say you take 1s state, okay, and it's a three-dimensional ball, right? If you just cut it through and plot it, you will get something like this. Okay? Any other questions? So what this bound state is modeling is an electron that is bound to the nucleus. Now let's put two atoms together. Let's put two wells. So we have a particle in a well. Now we have two interacting wells. Well, interacting, not the wells are not interacting. The electrons inside are interacting with each other. So you have a model of hydrogen atom here, which has certain energy, right? By the way, I skipped that part of the code, but if you look at here, it's eigenvectors. I'm plotting the eigenvectors, but I'm adding the eigenvalues so that the zero of the plot is the level of energy. That's why you see them like that. Okay? All right.
I think different units. Yeah, different units.
They have different units, exactly. But it's a convention to plot particle in a box states like 1 hump, 2 humps, 3 humps. Even in high school books, you would see them like that, right?
They don't have different units. Like they function as units of 1 over length square, but you need to see the energy on the y-axis. So
Just general, any image that you open would usually give them like that. Do you see? Like the energy, the bottom level, the first excited state, the second excited state. By the way, you might ask me why it's not going like a sine, because this one is sine squared. Like this one is the probability. It's psi squared. That's why it's 2 humps, 3 humps, which is also nice. We can do it as well, but let's not do it. Now, what I want you to think about now is what happens if you put two wells together. So I have these two wells that are identical, and electron living in this well has this much energy. Electron in this well has this much energy. That's the level. What happens if you bring those two hydrogen atoms close by? How will this electron interact with the other electron? we are moving towards sort of a bonding theory, how molecules bond together. So far, what quantum mechanics told us is that why hydrogen atom, for example, have those levels of energy that we see if we look at the universe. There's lots of hydrogen in the universe, and when you look at a gas cloud full of hydrogen, you will get certain. So hydrogen potential has certain energies, right? And depending on these energies, it will shine out light that has this much energy, right? So we have experimental confirmation of this effect with the light that we observe coming out of hydrogen atoms. Now we are thinking about hydrogen molecule. Two hydrogens come together. How do they bond, right? Now, we have two wells. Where are you? Artun, right? Artun, right? Artun. Do you remember our single well? Now we have a V negative and V positive. V negative, so we have a distance, let's say 10 angstrom. And at a distance of 10, we are putting one to the left by 5, one to the right by 5, okay? And that's creating the potential. Let me just, am I plotting something here? Let me not plot them, but plot this potential. Plot Vn. And let me also plot Vp. Okay. I guess yeah. Do you see those two potentials? One transferred a bit to the right, one transferred a bit to the left. Now, what we are going to do is we are going to create, so let me just comment this out. We are going to create a double well potential by adding them up. Let me plot also this one. Oops. Okay. I should really put the diagonal of this one. Or how do I plot the diagonal of this one? Should I do it like this? Or the first one was correct? Let me just check. If it doesn't work, no worries. Yeah. Do you see the? So I have a now potential that has two wells like this. Now let's calculate. Let me comment this out. Are you following? Yes. Let me draw the eigenstates when I have this potential. So you see these, there were two electrons that were at a certain energy level, right? They were like one electron is here, one electron is here. When you bring them together, their energy is split. They were at, both of them were at E, right? But now there is less energy corresponding to bonding and higher energy corresponding to something called anti-bonding. Okay? So now we are thinking of it as, the way that we solved it is actually we are treating it as single electron, right? We have one Hamiltonian that has double wells, and we solve that Hamiltonian. Instead of getting just one electron over here, we are getting this one plus that one, which has lower energy, and this one minus this one that has a bit higher energy. That's what's going on. Okay, let me switch to widgets so that we can get a closer look at this. Do you see there is a bonding state that has just a little bit lower energy. Remember, I'm shifting them according to their energies. And there is another one that has a bit just slightly higher energy. Okay? So since we see that it's sort of adding and subtracting those two things, the question arises, can we understand this double well potential by actually taking the linear combination of orbitals? What do we mean by that? So when I have a single well, I have orbitals, right? 1s, 2s, blah, 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 right? When I have double wells, I have 1s here and 1s here, but when you put them close together, somehow the bonding is it looks like to be 1s plus 1s, and the antibonding seems to be 1s minus 1s. Does it make sense?
It does.
It does? How about to everyone else? Yes? Good. Now, let me go into this deep theoretical stuff now. Okay?
Can you write one well and one hump?
One well and one hump. Why on earth would you do that?
Why not?
Okay, let's do that. Yeah. So what happened is that this is acting as a barrier. So no one wants to go there anyways because it's barrier everywhere anyways. So there's just this one. Okay? Are you thinking about the same thing? What if you have both of them like that?
Or like three of them and two barriers, one well.
Yeah. Okay. This is something called double barrier resonant tunneling.
Okay.
Everything has a name.
My advice is to use
Yes?
resonant tunneling barrier.
Yes, double barrier resonant tunneling. Yeah. Yeah, something like this. So you know why it is resonant? Because as you can see, what we form in the middle is particle in a box. So there will be tunneling, but the tunneling will be quite efficient at particular energies, and those particular energies will correspond to particle in a well energy levels. Good? Nice device application. Like you apply voltage and it just have these humps at certain points. Okay, you get the idea.
Why is that there are particular orange one that's pretty high?
What?
In the graph.
Yeah.
There is one, all of them are clustered together, but in right there's one red function that is
Quite high?
It's probably the resonant one by chance.
You mean this one? I don't know. I'm just improvising here, so. But it seems like these are particle in a box energy levels. Let's put more levels. Okay. Yeah, seems like particle in a box energy levels, but then after some point they are just too energetic. Fun stuff, right? Let's go back to what we were doing. We were trying to understand this shift down and up. So we are going to really build this theory of linear combination of orbitals now. So buckle up your seat belts. Hopefully, we will go through it quickly. Linear combination of atomic orbitals. Of orbitals. Doesn't need to be atomic. Okay. So what I have here so this is the potential Vx, and on top of this we have the solution phi x. Okay, we will focus on one orbital, so single orbital, just the ground state, and see what will happen. So the structure that we are trying to build looks like this. I have now two wells. And basically, I will represent these wells in terms of two functions. This one is psi x minus L, or should I call it plus L? It should be psi x plus L, right? When you add it, it shifts to the left. Oh, you are super bored already. Who is super bored? No one? You are so polite. Thank you very much. So let me write down the equation for this one. Hamiltonian times this orbital equals to energy times orbital. Okay? Writing it more completely, there is some kinetic energy operator plus some potential, and then we have psi of x equals to some kinetic energy part plus potential energy part, psi of x. Now, when I have the second situation, when I have this double barrier situation, then I still have the kinetic energy operator, but now I have also x minus L, plus L and Vx minus L. Does this make sense to you? There are shifted potentials. Okay, acting on, now here is where we actually use the linear combination. We are going to say that let there be A times phi x plus L plus B times phi x minus L. This is an approximation. Let me say it beforehand. We are doing an approximation, right? Would you agree with that? Because it doesn't need to work like this. What we are doing is we are constructing this solution. We are approximating this solution as linear combination of single solutions. Good. Then it's equal to, it should be equal to some kinetic energy part plus potential energy part that is changed now. So in a moment I will claim that the kinetic energy part didn't change, but let me claim that soon, not now. Exactly. Now, can you tell me what happens? So let's say I have kinetic energy times psi x equals kinetic energy times psi x. Let's say this is the case.
Then it's a plane wave.
I don't like it. Sorry. I was going for something else. My point was this. Let me change my point. Do you agree that this will be the case? whether I operate, no, this is also not right. Should have thought about it more clearly. Just cut me a slack and let's cancel this out for now and concentrate on the potential part. I will make this part clear later on.
T psi x equals ek psi x. None of them are x dependent, so you can shift the x whatever you want.
Yeah, that was my idea, but T psi x is not E psi x.
Deal with them. T psi x is not equal to T psi x minus L, but T.
No, but T psi x is also is not E psi x. I just realized that. That's what's the problem here. I will tell you how this cancels out later on because I know that it cancels out. Okay. What cancels out is this. What cancels out is this. If I do psi x star t psi x, if I do this, actually, let me put dagger here. Do you understand what's going on here? Sort of.
Yes, this is scalar.
Then this is equal to psi x minus L t psi x minus L. Okay? Also with plus 1. And since I'm going to multiply the ultimate equation with psi x plus L's and psi daggers and whatnot, you will see it in a moment, those parts get cancelled out.
I have a question.
Sure.
Right now, is the psi wave function or vector?
We go back and forth between a function and a vector. Why do you accept my shaky answers?
Is the expression here psi dagger t psi?
Yeah. We should really, now that we talk in this language, we should really say that it's a vector. Are you happier this way? Yes. Thank you very much. You like rigor, but you don't push it. I like that. Anyways, my whole point here is this. My whole point. If I write it down, let's focus on the potential part. If I write the V plus as the plus shifted, V minus as the minus shifted ones, times A phi plus plus B phi minus equals to some potential that is going to come out from here, A phi plus B phi minus. So I'm going to get two equations now. I'm going to get two equations from this one equation. The way that I do it is I first multiply from the left side by phi plus dagger. Phi plus dagger. So what do I get if I do that? I get phi plus dagger V plus A times phi plus. Can you please control my algebra?
It should be a squared.
Why?
Because they are.
No, I'm just multiplying with phi plus dagger, nothing else.
Oh, all right.
Okay. Anything else? Plus dagger, V minus, V plus, phi plus. Then I have plus B phi plus dagger, V minus, phi minus, plus B phi plus dagger, V minus. Did I write the same thing twice?
The first one should be plus.
This one is V plus, this one is V minus. Yes. Equals to EP A times phi plus dagger phi plus EP B times phi plus dagger phi minus. Do you have any questions here? No? Well, I'm going to what is the other thing that I'm going to multiply this with? Can you guess? Phi minus dagger, yes. So once I do both of that, so I did the first one, assume that I did the second one. Let me get yet another notation. Let me call this VPPP. It's like plus, plus, plus. So this is, let's call this VPNP, plus negative, positive, negative, positive, okay? If I follow this notation, then I get this matrix equation. VPPP plus VPNP, VNPP, VNNP, VPPN, VPNN, VNPN, VNNN, AB is equal to this potential term times SPP, SPN, SNP, SNN, AB. Okay? Good? Did you ask what is this? S. What is S? S, I didn't define S. This is SPP, and this is SPN. Now, S is something called orbital overlap. Okay, so how much overlap do you have between two orbitals? Now, if you do psi plus dagger psi plus, what do you get? Actually, we know SPP exactly. 1. Because it's just a wave function dagger times wave function. Did you follow that? But the others are smaller. The others are smaller. Just so happens that we have a code for it. So remember now we can go back and tell you what was going on here. So before, when we had a single well and single orbital, we have defined Fs corresponding to single wave function. Okay. Then over here we have also defined that single wave function shifted to the left, so that's Fn, right? And shifted to the right, that's Fp. Now VPP is Fp conjugate transpose dagger, right? Times Vp times Fp. Good? Yeah. Did you follow all this? And you have all this over here and all this over here. Now, how are you going to get the solution to this equation? Well, you can take the inverse of this one, multiply it from the left side, and solve the eigenvalue equation. Okay, that's what we are doing. We have a matrix that is composed of these elements, and we take the inverse of S matrix, this matrix, multiply it with V matrix, and take and that will give us the potential energies. And the kinetic energies are just F single time conjugate transpose times T times F single. Let's actually try whether this works, because I promised you that this one, EK1, should be the same as this one, right? So let me call this E2. Let me just print ek1 and ek2. I haven't done this, so if it's wrong, ek is not defined. Okay. Did it print? Oh yeah. It's actually printed here with complex values. So do you see that this number and this number is the same?
Yeah.
Yes? Okay, because I'm printing also other stuff here, let me just print their real values. There is always this small complexities. So the real values are well, they are the same. Come on.
Is there a way to solve this question without any matrix inversion? Because you know matrix inversion takes a lot of time. It's 2 by 2 now.
Yes, there's a way of taking it without inversion. You ignore that term, and we are going to do that as well. So you ignore the orbital overlaps. So let's look at the terms. Let me just stop printing this one, and let's look at VPP, VPNP, etc. If you look at them, the diagonal terms are non-negligible, these terms. Okay, VPP, VPNP. What are they? PPP, PNP. PNP is small, right? Almost zero. And finally, what I have here, PPN and PNN are non-negligible. They are there, right? And they are going to form something that we will call hopping integral. Okay? We are actually going to do something with it. Just trust me, please. But it's not going to get any easier. So let's have a break.